We spent a couple of days now talking about charge, positive charge, negative charge, why an object is positively charged, why it's negatively charged, what charges move and what charges don't move because of the electric force versus the strong nuclear force and so on. What I want to do today is talk about the way something gets a charge, the way something becomes either positively charged or negatively charged. There are two main ways of transferring that charge. One of them is called conduction, and one of them is called induction. Now, what I want you to remember is that conduction always, every single time, conduction always involves a transfer of charge. Now, that might seem odd to you to say it always involves a transfer of charge. You would think induction does as well, because how do you charge an object without involving a transfer of charge? Well, we'll deal with that in a few moments. But for now, just remember that conduction always involves a transfer of charge. Induction, on the other hand, will never involve a transfer of charge, which I'll explain in a few moments. Notice, though, I do have a little asterisk beside that, because in a certain context it never involves a transfer of charge, but in a bigger context it sometimes does involve a transfer of charge. But you'll see what I mean by that and why I said that it never involves a charge transfer in just a few moments here. Now, conduction, again, usually, not always, but usually involves touching. Whereas induction, well, will never involve touching. We don't need to put an asterisk beside that. We'll just say it never involves touching. So if you have trouble distinguishing them, forgetting which one goes with which, just remember that induction is the never one, the never charging, because it never involves a charge transfer and it never involves touching. If I walk across the carpet in my sock feet and I reach out with my finger and I touch somebody else's finger, you get a shock, right? I transferred charge to my body from the carpet by conduction. My feet were touching the carpet and there was a charge transfer. So that's clearly conduction. When I walk up and I touch you, that's also conduction. Charge being transferred from me to you, and it involves, usually at least involves, touching between my finger and your finger. Both of those are charging by conduction. Does that make sense? Versus charging by induction, which never involves that charge transfer and never involves touching. Now, let's talk about conduction in a little bit more detail. We can break that down into two categories, two subcategories. We'll call it charging by friction and charging by contact. Charging by friction will involve rubbing. When you rub things together, the balloon against your hair, when you rub the comb in your hair and your hair starts standing up on end, okay, when you rub something against something else and it becomes charged, charge transfers from one to the other, makes one of them positive, one of them negative, that's charging by friction within the overall category of charging by conduction. Charging by contact, on the other hand, well, we've already done this, really. We just haven't called it charging by contact. When one thing is neutral and the other thing is plus 10, and you touch them together and they balance it to be plus 5 and plus 5, that's charging by contact. Or if one is negative 2 and one is plus 4, add them up, divide by 2, get plus 1 and plus 1, that's charging by contact. The reason that I have the word conduction in brackets here is because sometimes we don't actually distinguish between friction and contact. Sometimes when we're talking about contact, we just call it conduction. The reason I have touching in brackets is because it doesn't actually have to involve touching. If I walk across the carpet and go to touch your finger and you get zapped just before our fingers touch, we still call that charging by contact. Charge is transferred, our fingers were close enough that it was as if they were touching, right? These didn't actually touch. So sometimes this can actually take place without touching. Another example of that would be lightning. When lightning forms, you get this big charge buildup on the cloud, right? Discharges to the ground, charge transfer to the ground. That's conduction, right? Well, the cloud wasn't rubbing against the ground. The cloud was close enough to the ground to transfer as if it was touching the ground. Was it touching? No, but it was as if it was touching. So we'd still call that charging by contact. Now let's look at charging by induction. There's two subcategories of charging by induction. One's called charging by, or creating a temporary separation of charge, and one's creating a permanent charge. I'll draw a couple of pictures for these. Let's say I have a neutral object. Equal number of positives and negatives, right? Bring a negatively charged object nearby it. What's going to happen to the protons in that neutral object? I'll give you a hint. There's a one-word, quick and easy answer for this. What's going to happen to the protons? Nothing. Because they're too tightly bound in the nucleus by the strong nuclear force. What's going to happen to the electrons? They're bound to the nucleus as well, right, by the electric force, but not as strongly. What's going to happen to those electrons? Not going to move to the positive per se. They're going to... what's going to happen to the negatives in here, that are already in the neutral? They can be pushed away from this, right? They get repelled by these negatives. So those negatives end up going, oops, didn't want it that big. Those negatives end up going over to the left-hand side. Not necessarily all of them. I draw it as if they all go over there, but they don't all go over there. It's just easier to see it if I draw it that way. This creates what we call a separation of charge. You can see the left-hand side of this is negative. Right-hand side is positive. See that? It's still overall neutral, but the charge is separated within this neutral object. How about this? Another neutral object. This time I'm going to bring a positive rod nearby. By the way, when I draw that as positive, I don't mean all positive. Some are positive, some are negative, but there's more positive than negative. What happens to the protons in the neutral object? One word answer. What is it? Emily? Nothing. Nothing. They're not going to go anywhere because of that strong nuclear force. What happens to the negative? Yes. They're going to get attracted to the right-hand side. I draw it as if they all go over there. They may not all go over there, but whatever. In the end, you can see that clearly we have one side that is positive and one side that is negative. Again, a separation of charge. Why do you think we call it temporary, though? You can see where the word separation comes from here, right? Where does this word come from? Why is it temporary? Yep. Yeah. If I move the charging object away, the rectangular rod, doesn't matter what the shape of that is, right? I just draw it this way. But if I move that thing that I have drawn as a rectangular charging rod away, the electrons are going to pretty much go back to where they were before, right? Evenly distributed. They repel each other until they're evenly distributed. So it's temporary, right? How do I make it permanent? How would I make it permanent? You guys ever heard of a ground wire? Do you know what it means when I say grounding something? Ground wire or grounding? Some places in the world they call it earthing, not grounding. It means the same thing. What is it? Not necessarily, although it could be. Yeah. You're thinking of your car? Yeah. Because your car can act as the ground in that case. Yeah. Yep. Yes. Yes. While you're trying to get rid of an excess charge or gain charge, either one. Usually get rid of, but not always. A ground is usually the earth. it's usually the ground, but it doesn't have to be. It can be any big object. I can sometimes, depending upon what I'm trying to ground, I can serve as the ground. If there's a little object over there that has a negative charge, and I walk over and touch it, I'll effectively ground it, drain the charge off of it. Okay? Any big object can serve as the ground, but usually it's the earth. Whatever I'm using as the ground, it's attached to, or it can be attached to the object via a ground wire. The ground wire has a symbol that looks like this. So I have these two objects grounded now. Maybe they're literally touching the ground via this wire, or maybe they're really small and somebody just walks up and touches them, but they're grounded. Okay? You have a ground wire in your house, by the way. Do you know this? The ground wire in your house is a copper wire that's a little bit skinnier than your baby finger. Sometimes if you go down to the basement, you can see it, like attached to a copper pipe. Sometimes if you're outside of your house, depending upon your house, I've seen them before outside of the house, exposed, going right down beside the power meter into the ground. Do you know where it ends? About 6 feet underground, attached to another rod that keeps it from being pulled up from the ground. That's it. Okay, the earth is big enough that if you have a short circuit in your house or some kind of extra electrons, they can be pushed down into the ground, and that's where they go, down into the ground. We just make sure it's 6 feet down so that it doesn't get pulled up easily, right? Kids aren't playing and pull up the ground wire and make your house susceptible to burning down now. It's just a source for electrons or a sink for electrons. Okay, what happens here now? I've got both of these grounded. What happens? Nothing happens with protons, right? What happens to the electrons? What happens to these three electrons right here? Wherever the ground wire is, these electrons are going to get pushed down by this negative into the ground. What do you see that I have here now? That's not a separation of charge. That's a charge, right? That neutral object is now positive. Except it's still temporary, because if I take that charging object away, what happens? They just go right back to where they were. How do I make it permanent? We're almost there. How do I make this permanent? Got to do one little thing. Yep. Disconnect the ground wire. Like literally cut the ground wire, or just take it away, disconnect it in some way. The electrons want to go back up where they came from, but they can't, because there's no path for them to go up where they came from. So now it's just positively charged. What about down here? Well, negatives aren't going to get pushed down by this positive. Negatives are going to get pulled up by that positive. So now you get a whole bunch of extra electrons in here. Now it's negative, right? How do I make it permanent? Quick, how do I make it permanent? Cut the ground wire, remove the ground wire. The electrons want to go back down, but they can't. They stay where they are. Now it's permanently negatively charged. One thing I want you to notice here, guys, is this. The side of the object that was neutral, should have mentioned this before, okay, when we had a temporary separation of charge. Let me redraw that, actually. When we had that temporary separation of charge, this was my negative. This is my positive. The side that was closest to the charging object is always opposite. Look, negative and positive. Positive and negative. That's why charged objects attract neutral objects, because the side that's closest becomes opposite. Charged objects attract neutral objects because opposites attract, and the side that's closest becomes opposite. Okay, does that make sense? That's still temporary. When I attach the grounding wire, then it becomes permanent. And attach the grounding wire and then cut the grounding wire, it becomes permanent. Make sense? Okay. In our last unit, we looked at things like collisions of cars, right? And that was like, see this, feel this, touch this, right? You gotta, even if you have never been involved in a car crash, you can picture that car crash and visualize what's going on, right? This is a little harder, certainly a little harder to visualize. I'm going to give you a couple examples to help you to visualize that, okay? Let's give you one, and then we'll give you a little bit of a break, and we'll give you the second one here. These are both on the example question handout that I gave you at the beginning of the unit, page 2. This is what we call an electrostatic precipitator. It basically filters air. Everybody has an air filter in their house, in the furnace of their house. You ever seen that? It's like a rectangular thing. Okay, every 3 months you switch it in and out. You just buy them at Home Depot or Costco or Walmart or something like that. It's a mechanical filter, right? These fibers in this filter are close enough together that they literally just trap particulates that are in the air, prevent them going through. You guys know that you have that in the floor of the rooms of your house. You have this small rectangular box. That's the heat vent, right? If you have forced air, which most people have is forced air, okay, that's the heat vent. But you also have these rectangular vents along the wall, the base of the wall. Those are cold air vents. They suck the cold air down into the furnace through the furnace filter, and then the air goes into the furnace, heats it up, and then sends it back up into the room. Okay? In the middle of all that, you get this furnace filter to clean the air. Hey, if you're going to circulate the air like that, you might as well clean it a little bit, right? Okay, that's the idea. But if you have one of these, it's better, because this is not limited by how close these fibers are together. If these fibers are pretty close together, then you're going to filter pretty small particles, but even smaller particles are still going to go through. So you're still going to get pollutants going through the furnace and back up into your house. But this does a better job. We're not limited by size. This is an electrostatic precipitator. It uses electricity to filter out particulates like dust and so on. This is a battery down here, or some kind of power supply. You see the symbol for battery looks like this. The small side of it will always be negative, and the big side will always be positive. Okay, that makes these blue rods negatively charged. They're close to the negative side of the battery, so they become negatively charged. I'm not sure if you can see that in the photocopy that I gave you. If you can't, then make sure you label that, because that's important. These red plates are positively charged because they're close to the positively charged terminal of the battery. This is air. This air is being blown through this precipitator by a fan. That air contains particulates like dust particles and so on right here, but they're neutral. Those neutral dust particles, along with the air, go through these blue rods that are negatively charged. Lots of them touch these blue rods. As they touch these blue rods, they become what? Neutral touches negative, the neutral becomes negative, right? The neutral becomes negative. That's called charging by what? Yeah, charging by conduction or charging by contact. Good. So now you can see these dust particles are negatively charged by conduction or by contact. Now these negatively charged dust particles go through the positive plates. What happens? They get pulled towards it. They get attracted, right? So positive attracts negative. These negatively charged dust particles get fixed to this positively charged plate. What goes through the other side? Air, right? Air minus what? Dust. Air minus the pollutants. Right? Does that make sense? Okay. Even if these dust particles went through neutral, these positively charged plates would still attract a lot of them. But if we can make some of them at least negative by touching these rods, then we're going to get a higher percentage of them. Right? Yep.
What if the air molecules went by and touched the negative rods? Would that be attracted to the plate?
It's a good question. I'd have to say no, because otherwise it wouldn't be a very efficient thing, right? So I'd have to say no. I think I'm not sure. I can't answer why that would be though. It's a good question, but I'd have to say no. Otherwise this wouldn't work. It wouldn't be very effective, right? Yeah. Okay, that's a really good question actually. If we switch the charge of the rods and the plates, basically by switching the battery to look like this, right? Yeah, It would still work, except that these dust particles that went through wouldn't become negative, they would become positive by conduction, and then they would be attracted to the negative red plates. Does that make sense? So it doesn't really matter what charge they get. Another example, also on the second page of your note package, sorry, on the second page of your example question package, this would be an electrostatic painting example. See the picture on the board there of the pool and the ocean in the back and the nice wrought iron fence. That's my backyard after I win the lottery tomorrow night. That's what my backyard's going to look like. But I notice in my backyard that the fence in my backyard, this steel fence in the backyard, it's kind of chipping a little bit. I want to repaint it, but I'm too lazy to just use a brush because it's going to take forever. And I'm too cheap to pay somebody to come in and paint it. Now, I know what you're thinking. You're rich because you just won the lottery tomorrow night, right? I'm still too cheap. That's how you save your money, right? Is don't pay people to do stuff like this. So I want to do it myself, but I don't want to do it by hand because I'm too lazy to do that. So I get this new thing, an electrostatic painter. This electrostatic painter has this rod in it. This rod becomes charged electrically, right? Either positive or negative. We'll call it negative, although it doesn't really matter. It's plugged into the wall, okay, or it's got a battery. You can make it negatively charged, this rod. Now this tube goes down into a container of paint. And there's an air compressor that's going to blow this paint up, move this paint up through this gun, past this negatively charged rod, and then out the nozzle at the end. When this paint comes out the nozzle at the end, what's special about it? It's negatively charged. How did it become negatively charged? By that rod, right? It touched that negatively charged rod. So the paint is negatively charged because it touched this negatively charged rod in there. So in other words, it charged it by conduction, charge it by conduction or charge it by contact, right? The electrons move from the rod to the paint. Paint is negatively charged. Now, if this paint was neutral and I was blowing this paint at this fence, some of the paint would touch the fence and make a pretty good coat on one side of the fence, right? But a lot of it would go right through the openings between the slats of the fence, right? You waste a lot of paint. Remember, I'm cheap, right? Yeah, I don't want to pay somebody to come in and do this. I also don't want to waste a lot of paint here either. So I don't want neutral paint. I want charged paint. Let's say negatively charged paint. If I have negatively charged paint, some of it still strikes the front of this fence and paints it nicely, but the part that misses, or at least some of the paint that misses, that remember is negatively charged, that was going kind of around it like this, ends up being attracted to this neutral fence slat there. Some of this gets attracted to the neutral fence slat. So it serves a couple of purposes. One, we get better coverage, right? Some of this paint, I can actually paint part of the back of this fence from the front. Certainly the side of these slats from the front. So we get better coverage, more even coverage. And we also, what's the other benefit of it? Safety, sure. Sorry? Save paint for sure, yeah. Which is a cost savings, right? A huge cost savings. Especially if you're doing this on mass scale, right? You do something like this if you're painting a car, right? If you, at a factory painting a car, they would do something like this so they would waste less paint, a lot less overspray and a lot less paint wastage. And if you're building hundreds of thousands of cars, then you're going to save a lot of money by using half the paint for each car. Make sense? Now, by the way, this paint is all charged, right? So isn't that going to make my fence charged? Walk up to the fence, try to open the gate, and get zapped? It might be, actually. It might be kind of fun. But how do we prevent that? I don't have to really do anything special. Not in this particular case. In some cases you might, but not in this one. Why not? The fence is grounded, right? I don't need to worry about a charge buildup on this fence because it's already grounded. It literally goes down into the ground. Make sense?